Hey, welcome back, everyone. Let's continue our discussion of soft margin SVM. Actually, before we do that, let's do a recap for all of support vector machine. So in the beginning of support vector machine, we presented it as a classification method. And the way it's done is to maximize the margin, and we discussed the geometric intuition and the math behind all of this, right? So for example, the SVM is trying to determine a linear decision boundary that separates the two classes, and this decision boundary should maximize the margin, right? So we kind of talk about the intuition as well as some of the math behind the geometry of the problem. Next, we derived and simplified the primal problem. So this was basically this whole process of continuing our geometric understanding of the problem and translating it back and forth between math and geometry, and then going ahead and formulating a constraint optimization problem whose solution is going to give us the hyperplane, right? The hyperplane is parameterized by a vector w and b. So we simplified this quite a bit, and this is kind of where we got to. So this is a primal problem. Afterwards, we derived, so actually we first talked about the generalized Lagrangian function, as well as the dual problem for a general optimization problem. We then specialized our discussion to deriving the dual problem for SVM. So here, this was the general introduction, where we rewrote the constraint optimization as simply an unconstrained optimization of the generalized Lagrangian. And then we kind of wrote down our constraint optimization in one line, which had a min and a max. And when we swap the min and max, we actually get the dual problem. We applied this idea to the SVM to obtain the dual form of the SVM, which is down here. Next, we kind of used Slater's condition to show strong duality. And this basically means that when we solve the SVM primal problem, like when we solve the SVM problem, solving the primal problem is actually equivalent to solving to solving the dual problem. And we kind of analyzed the dual problem a little bit. And starting from solving the dual problem, we obtained lambda star, and then using lambda star, we went back to the primal problem to obtain our W star and B star. So in the end, we were able to solve the SVM problem. We then interpreted the optimal solution using KKT conditions. In particular, we looked at the last condition of the KKT conditions, which is called complementary slackness. And that basically allowed us to kind of formalize the intuition behind support vector machines, where we have some support vectors which are on the margin that solely determine the hyperplane. And all of these points, they can actually move around a little bit without affecting the hyperplane, right? And the reason was that all of these support vectors have associated lambdas have associated non-zero lambdas, whereas these other points had dual variables lambdas that are not that are actually equal to zero. So they don't really contribute to the decision boundary. Okay, so that was kind of a long discussion about, first of all, explaining the intuition behind SVM, looking at both the primal and dual problems, and finally using the theory of optimization, taking advantage of strong duality, we solved the SVM problem. And then we interpreted the SVM solution as well, right? And finally, we said that, okay, so maybe using directly the data points doesn't always make sense. So why don't we use kernels? And using kernels was actually a more computationally efficient way compared to using features, but it's actually equivalent to using features. And finally, we talked about soft margin SVM, which we will continue to discuss today. In particular, we began by comparing the original SVM called vanilla or hard margin SVM, which basically kind of maximized the margin equivalent to minimizing the 1/2 the square 2 norm of W subject to this constraint. In contrast, for soft SVM, we add a penalty term and we add some slack to the constraints. And the slack variables are basically these C variables, which allow some violation of the original constraint, right? So originally we said left-hand side must be greater than or equal to 1. Here we're saying, okay, you're allowed to be a little less than 1 by the amount of C, right? And where C is non-negative, of course. And however, if you violate the original constraint slightly, you're going to pay for it up here in the objective. So that's kind of the intuition behind soft margin SVM. So everything, so here in the diagram on the left, we have the decision boundary in black. The plus and minus 1 planes are basically all the points such that we have yi times W transpose xi minus b is exactly equal to 1. So any red point that is on the right side of the red line, the plus 1 plane, are going to incur some cost in the form of Cj. And any blue point to the left of the minus 1 plane in the diagram will incur some cost in the form of these Ck variables here. Right? All of the other variables, they already satisfy, all of the other data points already satisfy the original constraints, so they do not incur any additional cost. Okay, so one thing to note in this picture is that suppose I have a red point which is at my cursor right here, over here. So if I had a red point here, we will actually incur some cost because it's to the right of the red line, right? It's to the right of the plus 1 plane. However, it is actually still correctly classified. So in soft margin SVM, it is actually possible to incur some cost, even though the data point is correctly classified. And in these cases, we're incurring the cost because the data point is actually below margin. It's kind of within the region where originally there should not be any points. Okay, then we proceeded to do some math to simplify the soft margin SVM optimization problem. The first step was to move everything to the right-hand side except for Ci. So then now we have two constraints which both involve Ci greater than or equal to something. Because the constraints must be simultaneously satisfied, these two constraints can be simplified to a single one involving the max C greater than or equal to the max of the previous two right-hand sides. Okay, and then the next step is, while we're penalizing Ci anyway, and there's no reason for Ci to be any greater than the right-hand side here, so we can move the max right into the sum. And that basically removes any constraints, and our problem becomes an unconstrained optimization problem. We then rewrote, kind of just rearranged the terms, and we basically put the summation first, and the plus 1/2 W 2 norms of W squared after that. And then we kind of just fiddled around with some constants, so basically dividing by gamma, because that doesn't affect the optimal solution. And then we renamed 1/2 gamma to be lambda. And now the problem kind of looks like some kind of loss function, which is summed over all the data points. So we have seen this before for the square loss. And then plus something that looks very much like a regularization term. So this is where we're going to continue our discussion. Before that, let's quickly do an in-class review. So take a look at this. So consider a linearly inseparable data set. So the data set cannot be separated perfectly using a hyperplane. Which of the following statements is true? So let's take about 2 minutes to think about this. Okay, let's take a look. So remember that we're given a linearly inseparable data set. So first one, hard margin SVMs with linear kernels never have a feasible solution. So this one is true because the data set is linearly inseparable. So that means that it's actually impossible to satisfy all the constraints. The constraints are actually just saying that the data points from one class must be all separated from, must all lie on one side of the hyperplane, whereas the data points from the other class must lie on the other side of the of the hyperplane, right? So while we're given that this is impossible, so that's why the first one, A, is true. Okay, let's look at B. So hard margin SVMs with quadratic kernels sometimes have a feasible solution. So this one is true because even though the data set is not linearly separable, if we use a kernel, which is equivalent to introducing some features of the raw data points, we may be able to transform the data point into kind of a linearly separable data set in the feature space. So this one is true, but the next one is false because the next one is saying quadratic kernels always have a feasible solution, right? So not always. If your data set is such that with the quadratic kernel, the data becomes linearly separable, then hard margin SVM would have a solution. But this kind of depends on the data set, so not always. Okay, next, the remaining three all talk about soft margin SVMs. So remember that soft margin SVMs do not have any constraints. That means that we're allowed to pick any parameter, and the only goal in the optimization is to pick parameters that minimize the objective function, right? There's no constraints. There's no restriction on what parameters we can pick. So all three of the statements involving soft margin SVMs are all true. Okay, so soft margin SVMs, regardless of the kernel, will always have a feasible solution. And E is kind of a trick question, I suppose, because yeah, sometimes it has a feasible solution. Well, it always does. So by default, because F is true, E is also true. Okay, so hopefully you got most of that or all of that. Okay, so let's continue our discussion about soft margin SVM and let's look at this loss function because a bit more closely because it kind of resembles what we have seen before. So let's continue on the written notes. So the last step that we did last time was basically to rename the 1/2 gamma as lambda. Now if I just rewrite this by changing the order, I will have something that looks like this. Sum over all data points of max of 0, 1 minus yi, w transpose xi, minus b, plus lambda times the 2 norm of w squared. So this very much looks like, well, first of all, we have this penalty term, the L2 regularization penalty term here, right? This is like L2 regularization. It looks like it. And then this part is a label. And this part is model prediction. Prediction, right? We would usually call that y hat. So a more general version of this is actually, and then sorry, this entire thing is then the loss function. The form of loss function looks like this. So the objective looks like this, which is min over w and b. of summation over the data point. So we have seen this before. We used to sum over the data points when we had the square loss, right? So this is just another version of a loss, which is not the square loss. And then we still have the regularization term. So this looks like sum of some loss function, which is going to be a function of yi, the label, and the model output, parameterized by w and b, plus some regularization. In this case, we have L of yi and y hat. So this part is y hat is equal to max between 0. So max between 0 and 1 minus y hat. This is called the hinge loss. Like before, we can always simplify the w and b. So remember here we have w of xi minus b. That's our model. But we can kind of do, you can easily change this to just w transpose x if you really wanted to, right? So we know how to do that. We can just introduce the 1 into the feature, an extra 1, and then we can just move the b inside w. So I guess more simply, we can remove the b. We can always, we can remove the b by redefining w and x. Hinge loss, so now we basically have something that looks like what we had before, but we're using the hinge loss for SVM. But previously, we actually had L of yi, actually L of y hat. So this is kind of for any data point y, L of y hat. Previously, we had y minus y hat squared. So that was the square loss, right? So square loss for least squares. So basically, when we do soft margin SVM, it turns out that our loss function, after some simplification, simply just becomes the same form as the square loss, L2 regularized square loss, except that our loss function, without the regularization, is the hinge loss, not the square loss. So how does the hinge loss compare to the square loss? So to see that, we're going to draw a graph. In the graph, in the horizontal axis, we have y hat. And in the vertical axis, we have the loss function L of y hat. So basically, we're going to specialize the case. So remember, we're going to specialize to case of binary classification. And that means that y can only be 1 or minus 1. So let's take a look at the hinge loss. The hinge loss is actually max of 0 and 1 minus y hat. So 1 minus y hat looks like this. So it has a slope of -1 and an intercept of 1, right? So it's basically gonna a line that looks like that. Actually, I'm gonna use a different color. So it's a line of slope 1. until we get to negative values for the line. In that case, when one minus y hat is negative, the 0 becomes the maximum, and we basically have a flat line afterwards like that. So what this is saying, so this is max, the green curve is max of 0, 1 minus y hat. So what this is saying is that in the hinge loss, if we have if the correct label is 1, and we predict something that is 1 or bigger, right? So the right hand side here is basically when y equals to 1 and y hat greater than or equal to 0, right? So this means that we have the correct prediction. So when that happens, we incur no cost on the right. Okay, let me get the axis back. We incur no cost to the right. And we incur a little bit of cost in this segment where we're making the correct prediction, but then we're within margin, meaning that the data point is actually below the margin. So of course we have two different cases for correct prediction, right? The other way is that y equals -1 and y hat less than or equal to 0. But when you multiply, so that's why we're using the y hat. That's why we're using y hat as the horizontal axis, because it captures both cases when the correct label is 1 and when the correct label is -1. So yeah, so on the right side we have the correct prediction. On the left side, we have y hat is negative. That means that we could either have y equals to 1 and y hat less than 0, or y equals -1 and y hat greater than 0. So in both cases we have incorrect prediction. So what happens with incorrect prediction? So as you can see, the more negative y hat is, so the more wrong. So I guess if we look at the y equals 1 case, the more negative y hat is, the more penalty we'll get. So you could argue whether that makes sense or not. So I'll let you think about that. But I guess one good thing is that on the right side, we usually do not incur any cost for correct predictions unless we're below margin. For the incorrect predictions, we're incurring a cost that is linear in terms of how incorrect it is. So just to clarify, remember that y is equal to 1 or -1, but y hat is from a model, right? Y hat could be anything. So if y hat is really negative, for example, well, then we'll incur a higher cost if y is 1. So now let's compare this to the square loss. So what would happen if we use the square loss? What would happen if we use the square loss to do classification? So in order to look at this, we have to do a bit of math first. So let me make some room. Okay, I'm going to start writing on the right side here. So we know for square loss, L of y hat equals to y minus y hat squared. So actually I'm going to do something a little dumb, and I'm going to write it in two cases. And this is because we are specializing to the case where y can only be plus or -1. So in the case when y equals to 1, the loss function, the square loss becomes 1 minus y hat squared. I'm just plugging in 1 into y. When y is minus 1, we have minus 1 minus y hat squared. And I'm just going to simplify this a little bit more. So the first case is 1 minus y hat squared when y equals to 1. In the other case, minus 1 minus y hat squared. When we square something, we can make the inside negative and then square it, and it doesn't matter. So we can actually write 1 plus y hat squared when y equals to minus 1. Okay, so actually, if you stare at this for a bit, you'll realize that this is exactly equal to 1 minus y hat squared. Because when y equals to 1, we kind of have a y hidden in here, right? We have a 1 hidden in there, and the 1 is the y. And then when y is minus 1, we kind of have a minus 1 hidden in here. So it turns out that we can more compactly write the previous expression as simply 1 minus y hat, all of that squared. And this is convenient because our axis is y hat. And this allows us to draw this loss function very easily on the graph. So 1 minus y hat squared is a parabola that opens up. And I guess if you really want to make it really clear, we can write y hat minus 1 squared if you want. Right? So this is basically a parabola that opens up, and it's centered at 0, 1. So it's centered here, and it's going to cross. So when this part is 0, when we plug in 0, we get 1. So it's going to cross this point as well. However, it's a parabola, so it's not linear, and it looks more like this, right? Again, not a good artist, but hopefully you get the idea. Okay, so let's put arrows on all the functions. So what exactly is the square loss doing if we use it for classification? Well, in the part, actually let me write this, let me label the function as well. I guess I have to go back to the other color. So this is 1 minus y hat squared. So in the region where we have correct prediction, in this region between 0 and 1 over here, we have kind of a similar cost, maybe a bit lower. But on the right side here, on the right part of the parabola, we're actually penalizing predictions that are too correct, right? And that doesn't really make sense. When a prediction is correct, we should just not penalize it as much as we can. Yet the square loss is penalizing predictions that are too correct, so that doesn't make sense. On the left side, for incorrect predictions, over here, we're still penalizing predictions that are too incorrect in some sense, right? And even more so compared to the linear curve in green here, which is the hinge loss. So I would say that for the square loss in both cases, I would say it would be inferior to the hinge loss for classification. Obviously for regression, square loss is something that we used a lot, right? But it's not very suitable for classification. So, I mean, I guess that brings us to the question of what would be an even better loss compared to hinge loss, right? So we did see that on the right side with the correct prediction, the hinge loss seems to make sense. But the left side seems to also be penalizing predictions that are too incorrect, which maybe we don't necessarily want to do that, right? Because if you penalize predictions that are either too correct or too incorrect, your model would be sensitive to outliers, right? You could have one outlier that is extremely incorrect, right? You might get a y hat value of that is extremely large or extremely small that would actually affect your model a lot. So we actually don't want to over penalize kind of any predictions that are too incorrect. So therefore, based on that argument, I would say that the best loss to use for classification is to not penalize at all when the prediction is correct, and then penalize a constant amount. Let's just say the amount of 1 when we have a wrong prediction. So this is actually called a 0-1 loss. So that would be actually the ideal loss function for the classification. We're basically counting how many times we misclassified the data points. So unfortunately, it turns out that it is not possible or very, very difficult to optimize the 0-1 loss. The 0-1 loss is not continuous and therefore not even differentiable. It also has zero derivative everywhere, right? And it's also non-convex. So it turns out that it's actually NP hard to optimize the 0-1 loss. And if you look at this, if you look at these three curves, red, green, and blue, you will kind of see that the green curve, which is the hinge loss, is the best convex approximation of the 0-1 loss. So even though it is not exactly what we want, it's as close to what we want as we can get. So let's take a look at this again on the slides. So we have shown that for SVM, we ended up getting a loss function that looks very much like the square loss. The only difference is that this first L term is actually not the square loss, it's actually the hinge loss, right? But we're still summing over all the data points and then adding some regularization term. So what we're doing, so what we did is just to compare this L function for the square loss or enriched regression versus what we're doing in classification with the hinge loss. First, we did a bit of math on the slides, and basically we start with L of y hat equals y minus y hat squared. And it turns out that we can write this as 1 minus y hat, all of that squared, in the special case where y is only equal to plus or minus 1. The way we can see this is to try both. I guess we did it a different way on the written notes, but on the slides, we're going to do it in a different order. So let's just start from the 1 minus y hat squared, plug in plus minus 1, and we do get the two cases where when y is equal to 1, we have 1 minus y hat squared, right? Just plugging in 1 here. And when y equals to negative 1, we have 1 plus y hat squared. So that is actually 1 minus y hat squared. If we look at it from the other side, if we start with the square loss, y minus y hat squared, when we plug in y equals to 1, we get 1 minus y hat squared, which matches the first case. And when we have y equals minus 1, we have minus 1 minus y hat squared. That's the same as 1 plus y hat squared, same as the second case above. So this basically rewrites the square loss into a function of y hat, again in the special case when y can only be plus minus 1. And that allows us to directly compare with the hinge loss on this graph, where the y-axis is L of y hat and the x-axis is y hat. Plotting the hinge loss, we can kind of see in green that we have a negative 1 slope coming down until we get to the point 1, 0. And then it goes flat because of the max with 0. This means that on the correct prediction side, we receive no penalty unless we're within margin. In the incorrect prediction side, we receive an increasingly larger penalty based on how wrong our prediction is. Again, how wrong the prediction is depends on the value of y hat as predicted by our model. Again, y can only be plus minus 1, but y hat, which is produced by the model, W transpose X, it could be arbitrarily large or arbitrarily small. Okay, so what about the square loss? Well, the square loss is 1 minus y hat, 1 minus 1 minus y hat squared. So that's basically this parabola over here. If we used the regression, a loss that we typically use for regression, directly transfer over it for use in classification, then it doesn't work so well because it will over penalize the predictions that are too correct, which is not desirable, and at the same time penalize the predictions that are too incorrect as well, and much more so compared to the hinge loss. So the hinge loss is a much better loss for classification. Okay, so we can summarize a little bit over here, right? So I guess I kind of just said this. So we can directly compare ridge regression to soft margin SVM, and the only difference is going to be this L function that we sum over every data point. Right, we plotted the two loss functions as here, and our conclusion was that ridge regression penalizes predictions that are too correct. So it's actually very sensitive to classes where the data points are very far apart, right? So you could have a lot of data points that have the same class, but are very spread out in the feature space, right? So in that case, you will get a lot of penalties in this region for ridge regression, of course, not for hinge loss, not for soft margin SVM. On the incorrect side, the square loss penalizes predictions that are too incorrect much more harshly because it's squared, right? So it's also sensitive to outliers. The ideal loss is shown in the blue curve over here. We should be penalizing by the amount of 1 for all incorrect predictions and then not penalize at all for correct predictions. So we drew this picture earlier, but the mathematical form is that L of y hat should be equal to 1 when y is not equal to sine of y, i.e. when y hat is negative, and 0 when y hat is positive. So if we use this 0,1 loss, then this summation over the data points is basically the number of training examples that the classifier got incorrectly, I guess. So this is exactly the classification accuracy, right? So this is exactly what we eventually want. Unfortunately, this function has zero derivative almost everywhere and is non-convex, so it's very hard to optimize. It's actually NP hard, as we mentioned. Okay, so it's actually very often in machine learning that there's some loss function, i.e. the blue one, that we really want in the end. However, we cannot optimize it. So we have to use what's called a surrogate loss. So surrogate means replacement. So we have to use a surrogate loss instead of the actual loss that we want. And the hinge loss is actually the surrogate loss to the 0,1 loss. A square loss would also be a surrogate loss, but not as good for classification. Okay, so that kind of brings us to another loss function called the logistic loss, which is, I'm not plotting it here yet. It's actually L of y hat equals log of 1 plus e to the power of minus y hat over log 2. So we're going to study this a little bit more. So when we use the logistic loss, we're actually doing what's called logistic regression, which is actually, despite the name, is actually a method for classification. Okay, but before we get into the math, let's take a look at the different results that we can get using the different loss functions for classification. So on the plots on the right, we have a data set with the red class and the blue class. The contours and shaded areas show us the value of the loss function. For the square loss, we can see that the shades get darker, progressively darker because of the shape of the square. In this case, we would expect the decision boundary to be somewhere between, the best linear decision boundary would be somewhere between the red and the blue data points, right? But because of the outliers over here, the square loss is actually not doing a very good job. The outliers end up shifting the decision boundary of the square loss function. So the decision boundary is basically where the square loss is 0, I guess. Sorry, where yy hat equals to 0. It's shifting it too much to one side because of the outliers in the case of square loss. For the logistic loss, which we'll be looking at next, it's doing a much better job. Despite all of these points being really far outliers, we still get a really good decision boundary, as good as possible at least, through kind of where the red, kind of between the red and the blue data points. If you use the hinge loss, we'll actually get a similar result. Okay, so let's move on to talking about logistic regression then. Okay, so in logistic regression, we use this model, f of xw equals to sigma of w transpose x, where sigma is the sigmoid function. Previously, we introduced the sigmoid function as an example of a commonly used activation function, but it's also used in logistic regression as well. So the sigmoid function is actually sometimes known as the logistic function. The parameters are w, and just to save us some trouble, we're going to assume that we have a 1 appended to the end of the vector x. So we do allow for a constant term. So this is almost a linear model. We first do an inner product between our parameters and the input vector, but then we kind of, I guess, activate it. Not really. We then plug in the result into some nonlinear function. So a model of this form is actually known as a generalized linear model. And the inverse, just a bit of a trivia, I suppose, the inverse of the nonlinear function is known as the link function. So in logistic regression, we basically have a special case of the generalized linear model where the link function is actually the sigmoid function inverse, which happens to be log of z over 1 minus z. Okay, and this function has a name as well. It's called the logit function, or just the logit. So a lot of terminology here. We're going to get to kind of the analysis in a bit. So one of the features of the sigmoid function is that the output is always going to be between 0 and 1. So basically what we're doing is that we take our input, inner product with the weights, and then we squash the result between 0 and 1. Probabilities are also between 0 and 1, so we often interpret the result of the output, the output of the model, as the probability that the label of the input is positive. Okay, yeah, so I kind of mentioned this already. So logistic regression is a bit of a misnomer because it's actually performing classification, not regression. Some other names for it are logit regression, logit model, or just logit, depending on the field. In machine learning, I think most people will call it logistic regression. Some more annoying terminology. So the logit, again, we said that this function is a logit, but then here we're saying that logit could actually refer to a logit or logistic regression. I guess when you read about it, you have to make the judgment depending on the context. So in machine learning, the word logit usually means this quantity, the log of z over 1 minus z, where z represents the probability of a particular label being assigned by the classifier. So if we simplify this a little bit, so if we take so remember z is the probability, which is basically sigma of w transpose x. So if we plug that in for z and simplify a little bit, we basically just get sigma inverse of sigma. I guess I'm not really showing every step here. Previously, I already told you that sigma inverse equals to this function, right? So now if you take the inverse function and then plug in the function itself, you would just get W transpose X. So in machine learning, logit really means the quantity W transpose X before we squash it between 0 and 1. So to make a prediction, we would just threshold the output of the model, and we would predict 1 if sigma of W transpose X, i.e. our model output, is greater than or equal to 1/2, and -1 if our model outputs something less than 1/2. And equivalently, this is the same as 1 if W transpose X is greater than 0, and -1 if W transpose X is less than 0. You can kind of see the equivalence by looking at the sigmoid function, right? So when the input is positive, we have a value greater than 1/2, and when the input is negative, we have a value less than 1/2. So basically, the decision boundary is actually W transpose X equals to 0. This is actually exactly the same decision boundary as with SVMs. In fact, the decision boundary is a hyperplane. Usually, to train this model, we use what's called the binary cross-entropy loss. Here, I'm just adding LT regularization just to be consistent with the previous discussion of square loss or rich regression versus soft margin SVM. And basically, this function is defined to be L of W equals to minus summation over all data points of y equals to 1. So y equals to 1 times log probability that y hat I equals to 1 plus 1 yi equals to -1 inside the Iverson bracket times log of probability that y hat I equals to -1. So this Iverson bracket is just the indicator function. This quantity is equal to 1 if the inside is true, and 0 if the inside is false. Okay, so we're not going to analyze the logistic regression in as much detail as we did for SVM, but we can look at some results. So to train in order to optimize this loss function, we will be using gradient-based methods such as, let's say, gradient descent, right? And then we can take a look at the results. So here we have the blue and red data points, and initially we randomly initialize the decision boundary, and after a few iterations, the decision boundary converges to something reasonable. This is actually the output of the sigmoid function. We can see that we have a 1/2 in here, and then 0 and 1 on the two sides. Okay, that's all for today. We're going to continue to look at logistic regression next time. So have a great weekend. See you guys next time.